With this lecture, we're going to start our mathematical physics series. And the first topic we'll start with is vectors. Okay, so vectors. So this is a topic that you would have background in studying in your school days, in your undergrad days. And we'll simply review some concepts here. So vector is something that has a magnitude and a direction. So the classic example is speed is a scalar, right? It tells you only how fast you're going. Okay, it's a scalar. Whereas a velocity is a vector because it tells you how fast you are going and in which direction you are going. Okay, in which direction you are going. So if you are moving in some direction, okay, if you're moving in some direction, let's say I'm moving a ball or something like that across at an angle. Okay, so let's take two axes. Okay, let's take two axes. This is the y-axis. Okay, this is the y-axis and this is the x-axis as conventions. So I'm moving at an angle. I'm taking a ball and I'm moving this ball at an angle. Okay, at an angle. Now this ball from this place, okay, from this place onwards, it has moved to this place now. This is the initial position. This is the final position. So this ball has now moved from this point to this point. That means it has covered some distance, right? It has covered some distance along the it has covered some distance along the x direction, and that distance it had covered in some time, so it will be some velocity. So it had some component of velocity in the x direction, okay, and it had some component of velocity in the y direction because from the it has moved from this point to, so it has moved from this point to this point in the y direction in some time, so it would have some velocity in the y direction, right, in the y direction. So now if you compute, okay, let's say let's say that, so now this, okay, so this is the vx is the x component and vy is the y component. So now the x component is multiplied by its unit vector, right? So write it here. So to write the vector, so vectors are denoted with this symbol. Write the symbol v. So with the arrow mark on top. So the x component is multiplied by the unit vector in that direction. Okay, the unit. So this vx is just a number, right? So the direction that it is in along the x direction is given by the unit vector along the x direction I. So I is the unit vector along the x direction I, and j, which we'll now talk about, are unit vectors. So these unit vectors, what they do are they have a magnitude of 1. Okay, so they don't affect multiplying it with some other number, but they have a direction. So the unit vector I has a direction in the x direction and j in the y direction. So if we write it as v y plus j. Okay, so that is what we have. So if we just have v, so let's say now this vx of I is definitely along the x direction, right? It's along this direction, and this v of y is definitely along the y direction, right? It's definitely along the y direction. This is vx of I, vx of I, and this is, and the and we have a the v vy component is definitely along the vertical. It's definitely along the vertical. It's definitely along the vertical. So now you can displace this vector from here to here. It doesn't affect the vector because you shouldn't change only the angle. That is, you shouldn't change the angle of this vector with respect to this vector, but you can displace it and you shouldn't change its length. Otherwise, the vector remains the same. Okay, so you can displace it from here. You can pull it out to be here. So now to find out the resultant. So find out the resultant. how would you find out the resultant of these two forces? So we have Vx in this direction going in this direction and Vy in this direction. So the resultant now we can find out by using this theorem, right? We have studied about the Pythagoras theorem. It says that Vx square plus Vy square. So the resultant is nothing but its resultant velocity. Okay, it's resultant velocity, and along which direction is the magnitude of its resultant velocity. So Vx is equal to V square. V square is nothing but the hypotenuse. It's nothing but the hypotenuse. So V is nothing but square root of Vx square plus Vy square. Okay. So now we can write now V. We found out V, and the unit vector. Now how do we specify? Now we found out only the magnitude. So the magnitude of V is denoted this way. Okay. So we found out only the magnitude. Now the direction can be given in two ways. Now the easier way I'll keep for the later, and now I can talk about the direction in terms of an angle. So I can say this angle is theta, and this theta angle is the angle between the vector V and V of x, Vx, the x component, or the x axis. So this theta angle, what is this theta angle? This theta angle is nothing but, we can write it as tan inverse of V of y by V of x, right? Tan inverse of V of y. But there is a simpler way to do it, because this V vector, write it here, V vector is nothing but the magnitude of V multiplied by the unit vector of, this unit vector is denoted by hat, unit vector of V itself. Okay. So now what will this unit vector be? The unit vector will be equal to V vector divided by its magnitude. So this is a way of specifying the direction as well in terms of the unit vector, V of V vector divided by the magnitude itself. But however, let us consider the case where we have to add two vectors. Okay, we have to add two vectors A and B, which are not in perpendicular angles to each other. Okay, where we are not in perpendicular angles to each other. Let's take this vector A. Now this vector is at some angle. Okay, so this vector is at an angle theta with A. A and B have an angle, are at an angle theta with each other. Now in this case, how would you find out the resultant? So in this case, the resultant is given by this formula. This C is the resultant, the closing side of this theorem is actually called the parallelogram theorem. Now this vector is placed head to tail with this, and this closing side, this C vector, is the resultant, and the C vector is given by C vector. The magnitude of C vector is given by A square plus B square plus AB cos theta. Okay, plus AB cos theta. So this is the formula to find out the magnitude when the angle is actually not 90 degrees. No, this angle is not 90 degrees between the two vectors. Here we have a acute angle. So in that case, how to find out? So any angle, this theta can be any angle. Now we can watch that this formula now reduces to our previous case when theta is equal to 90, because when theta is equal to 90, value of cos becomes 0. So this formula will reduce to a square plus b square. So it's neatly done. And I told you how to find out the unit vector. So the unit vector is found out by, again, unit vector we can find out by C vector divided by the magnitude of C. So this case can be done. So next is so far we introduced the x component and the y component, right? So now it's natural to generalize to higher dimensions. In mathematics, we talk about abstractions, right? So it might not have any connection to it does. 3 dimensions has we live in a three-dimensional world, so three-dimensional vectors make sense. But people extend it up to n components. Okay, n, you can have n components. So a vector, let's say a vector, let's call the vector v itself, can have a vx component I, vj component, sorry, vy component, and the unit vector j, and a third component, the third dimensional component, vz component. Oh, sorry, it's the unit vectors. Normally, the convention is k, and it can have up to n. It can go up to n. Okay, it can go up to n number of components, and it can have n some nth unit vector to represent that. And the formulas all remain the same. Okay, so to find out now the magnitude of v, you just have to do the vx square plus vy square plus vz square. It's natural to just generalize the formula and write it out. Okay, so similarly, even for the v hat, it's just the same. V hat, the unit vector is just the same way you can do it. So just like now, just like how we finish this up. Okay, so just like how we add numbers and uh, add numbers and multiply numbers, we can add vectors. Okay, we can add vectors. So always you have to, when you're adding vectors, you have to add only the components. Okay, we have to add only the respective components. Okay, because you can't add, so let's take the two-dimensional case. If you have, say, some vx component, you can't add it with the vi component. It doesn't make sense. Okay, but if you add it, if you have, there is another vx component like this, this is called vx1, let's call this vx2. So now you will get a, this component plus this component will be a longer line. Okay, this will be a longer line. So it makes, so this vx3 is vx2 plus vx1. So that makes sense. So you add components. So when you want to add vectors, you add the corresponding components. So if you want to add, say, let's take an example, a vector is equal to 3i plus 4j, add it with b vector, which is 2i plus 5j. So add this the components, write out the components, add the components, and write it out. So you get the resulting vector, the third vector C. So you have this is the addition. Similarly, you can subtract. You just subtract the respective components same way. And vector multiplication has two kind of multiplication. Okay, vector multiplication is two kinds. So you have a called a dot product. Okay, you have a dot product. So this dot product of two vectors is just represented, the resultant operation of a dot product is always a scalar, so you don't get a vector. So this dot product is just a1th component by b. So we've been using x and y, right? So I'll stick to that. So ax component multiplied by bx component plus a y component multiplied by by component plus the az component multiplied by bz component, and can be generalized to how many ever dimensions you want. And this is actually equal to nothing but the magnitude of a multiplied by the magnitude of b times cos theta, the angle, where theta is the angle between the two vectors. And there's another kind of a product called the vector product. This is called the vector product because the resulting answer is a vector. Here in this case it's a number, it's a scalar. So you multiply the components, you'll get only a number. But here you will actually get a scalar. So a cross b, the vector product is represented by this number cross. Okay, this is called cross. This is not into, this cross. And I J. Okay, this is a determinant. So this is some necessary background you need to have with respect to determinants. I won't be going into that too much. So when you study about matrices and determinants, you have studied about determinants. You have to just take the determinant of this three into three determinant. Okay, this 3 into 3 determinant. You'll get an answer. You will actually get a vector. So that is why this is called a vector product. So this is how it is done, vector multiplication.